In mathematics, infinite compositions of analytic functions offer alternative formulations of continued fractions, series, products and other infinite expansions, and the theory evolving from such compositions may shed light on the convergence, divergence of these expansions. Some functions can actually be expanded directly as infinite compositions. In addition, it is possible to use ICAF to evaluate solutions of fixed-point equations involving infinite expansions. Complex dynamics offers another venue for iteration of systems of functions rather than a single function. For infinite compositions of a single function, see iterated function. For compositions of a finite number of functions, useful in fractal theory, see iterated function system. Notation. There are several notations describing infinite compositions, including the following. Forward compositions. Fk, n equals Fk, Fk plus 1, Fn minus 1 Fn. Backward compositions. Gk, n equals Fn, Fn minus 1, Fk plus 1 Fk. In each case, convergence is interpreted as the existence of the following limits. For convenience, set Fn equals F1, n and Gn equals G1, n. Contraction theorem. Many results can be considered extensions of the following result. Contraction theorem for analytic functions. Let F be analytic in a simply connected region S and continuous on the closure S of S. Suppose F is a bounded set contained in S. Then for all Z in S where alpha is the attractive fixed point of F in S, infinite compositions of contractive functions. Let Fn be a sequence of functions analytic on a simply connected domain S. Suppose there exists a compact set omega S such that for each n, Fn omega. Forward compositions theorem. Fn converges uniformly on compact subsets of S to a constant function f equals lambda. Backward compositions theorem. Gn converges uniformly on compact subsets of S to gamma omega if and only if the sequence of fixed points gamma n of the Fn converge to gamma. Additional theory resulting from investigations based on these two theorems, particularly forward compositions theorem, include location analysis for the limits obtained here. For a different approach to backward compositions theorem, see. Regarding backward compositions theorem, the example f2n equals 1/2 and f2n minus 1 equals minus 1/2 for S equals z. Z less than 1 demonstrates the inadequacy of simply requiring contraction into a compact subset, like forward compositions theorem. Infinite compositions of other functions. General analytic functions results involving entire functions include the following, as examples. Set then the following results hold. Theorem E1. If n1, then Fnf, entire. Theorem E2. Set epsilon n equals, and minus 1, suppose there exists non-negative delta n, m1, m2, are such that the following holds. Then Gng, analytic for z less than r. Convergence is uniform on compact subsets of z. Z less than r. Theorem Gf3. Let Fn be a sequence of complex functions defined on S equals z. Z less than m. Suppose there exists a non-negative sequence beta n such that set. Then Gng for z less than r uniformly on compact subsets. Theorem Gf4. Let Fn equals z, analytic for z less than r0, with Gn, c beta n, choose 0 less than r0 and define an Fnf uniformly for z, r. Furthermore, linear fractional transformations results for compositions of linear fractional transformations include the following, as examples. Theorem LFT1. On the set of convergence of a sequence Fn of non-singular LFDs, the limit function is either a non-singular LFD, a function taking on two distinct values, or a constant. In, the sequence converges everywhere in the extended plane. In, the sequence converges either everywhere, and to the same value everywhere except at one point, or it converges at only 2 points. Case can occur with every possible set of convergence. Theorem LFT2. If Fn converges to an LFD, then Fn converge to the identity function f equals z. Theorem LFT3. If Fn f and all functions are hyperbolic or loxydromic Mobius transformations, then Fn lambda, a constant, for all, where beta n are the repulsive fixed points of the Fn. Theorem LFT4. If Fn f where f is parabolic with fixed point gamma, let the fixed points of the Fn be gamma n and beta n. If then Fn lambda, a constant in the extended complex plane, for all z. Examples and applications. Continued fractions. The value of the infinite continued fraction may be expressed as the limit of the sequence Fn, where as a simple example, a well-known result follows from an application of theorem. Consider the continued fraction with stipulate that zeta less than 1 and z less than r less than 1. Then for 0 less than r less than 1, analytic for z less than 1, set r equals 1/2. Direct functional expansion. Examples illustrating the conversion of a function directly into a composition follow. Suppose that for t greater than 1, an entire function with phi equals 0, phi equals 1. Then, example, by a similar procedure, example, and by inverting the composition, example, calculation of fixed points theorem can be applied to determine the fixed points of functions defined by infinite expansions or certain integrals. The following examples illustrate the process. Example. For zeta 1, let to find alpha equals g. First we define, then calculate with zeta equals 1, which gives alpha equals 0.087118118 to 10 decimal places after 10 iterations. Theorem. Let phi be analytic in S equals z, z less than r, for all t in 0, 1, and continuous in t. Set if phi r less than alpha zeta s and t 0, 1, then has a unique solution, alpha in S. With evolution functions, consider a time interval normalized to I equals 0, 1. ICAFs can be constructed to describe continuous motion of a point z over the interval, but in such a way that at each instant the motion is virtually zero. For the interval divided into n equal subintervals, 1 kn set analytic or simply continuous in a domain S, such that for all k and all z in S, and example 1 now, set an if exists, the initial point z has moved to a new position, t, in a fashion described above. It is not difficult to show that f equals alpha z plus beta, alpha 0 implies. A byproduct of this derivation is the following representation. And of course, if fc, then example 2 with f equals z plus phi. Next, set and tn equals tn, n. Let when that limit exists, the sequence Tn defines contours gamma equals gamma that follow the flow of the vector field f. If there exists an attractive fixed point alpha, meaning f minus alpha rho z minus alpha for 0 rho less than 1, then Tnt alpha along gamma equals gamma, provided if Cnc greater than 0, then Tnt a point on the contour gamma equals gamma. It is easily seen that and when these limits exist, these concepts are marginally related to active contour theory in image processing, and are simple generalizations of the Euler method's self-replicating series and product series. The series defined recursively by Fn equals z plus Gn have the property that the nth term is predicated on the sum of the first n-1 terms. In order to employ theorem, it is necessary to show boundedness in the following sense. If each Fn is defined for z less than m, then Gn less than m must follow before Fn minus z equals Gn. C beta n is defined for iterative purposes. This is because occurs throughout the expansion. The restriction serves this purpose. Then Gn G uniformly on the restricted domain. Example: set an m equals rho 2. Then r equals rho 2 minus greater than 0. Then, if z in S implies Gn less than m and theorem applies, so that converges absolutely, hence is convergent. The products defined recursively by z, m, have the appearance. In order to apply theorem, it is required that where, once again, a boundedness condition must support if one knows C beta n in advance, setting z r equals mp where suffices. Then Gn G uniformly on the restricted domain. Example: suppose that where, observing after a few preliminary computations, that z 1/4 implies Gn less than 0.27, then n converges uniformly.